The silence of the machines, closing the case on Fermi, the mathematician who dreamed of machines that dream. There is a particular kind of mind that arrives at the future not by extrapolation but by derivation, that looks at the present state of things and, through sheer logical pressure, is forced to conclusions that will not become obvious to everyone else for decades. John von Neumann was such a mind, perhaps the most concentrated example of it that the 20th century produced. He did not merely work on the problems of his era. He worked on problems that his era had not yet recognized as problems. By the late 1940s, von Neumann had already reshaped the architecture of modern computing, contributed foundationally to quantum mechanics and game theory, and played a significant role in the design of the devices dropped on Hiroshima and Nagasaki. He was at this point turning his attention to something that would seem, in retrospect, even more consequential, the question of whether a machine could reproduce itself, and if so, what the logical requirements of such reproduction would be. The question was not, in his framing, primarily an engineering problem. It was a logical one. Can any automaton, any rule-governed system operating on discrete inputs, construct an exact copy of itself? And more, can it do so in a way that also passes along the capacity to reproduce? Von Neumann recognized that this was the same question biology had been answering for billions of years, and he wanted to understand the abstract structure underlying it. He presented his initial ideas at the Hickson Symposium in 1948, in a lecture titled The General and Logical Theory of Automata. The full formal development, which occupied him through the early 1950s, was assembled and published posthumously by his colleague Arthur Burks in the 1966 volume Theory of Self-Reproducing Automata. By which point von Neumann had been dead for 9 years, killed by cancer widely attributed to his radiation exposure during nuclear weapons testing. The solution he arrived at was elegant and unsettling in equal measure. He demonstrated that a sufficiently complex automaton could be decomposed into 4 functional components: a universal constructor capable of building any described machine, a universal computer capable of executing any described program, a tape carrying the description of the machine to be built, and a copying mechanism that duplicates the tape for the offspring. The logical structure, he showed, was not merely analogous to biological reproduction, it was isomorphic to it. The tape was the genome. The constructor was the cellular machinery. The copying mechanism was replication. He had derived, from pure logic, the abstract skeleton of life, and this some years before Watson and Crick published The Structure of DNA in 1953. Before the molecular basis of heredity was understood at all. This is worth pausing on. Von Neumann was not a biologist. He arrived at the same fundamental architecture that evolution had arrived at through 3 billion years of selection, working from the other direction entirely. From mathematics downward into matter rather than from chemistry upward into complexity. The convergence is either a profound vindication of the idea that life's deepest logic is computational, or it is one of the more astonishing coincidences in the history of science. What von Neumann did not develop in any detail, and what would preoccupy a later generation of engineers and theorists, was the question of what happens when you take this abstract logical structure and ask it to operate not in a mathematical space but in the physical universe. His kinematic model, one of 5 variants he sketched, imagined a robot moving through a sea of parts, assembling a copy of itself from available components. The model was deliberately schematic. The engineering details were left as an exercise for the future. But the implication was clear: there was no logical barrier to a self-reproducing machine operating in physical space. The question was only one of complexity and available materials. It was Robert Freitas who, in 1980, first seriously confronted those engineering details. Working from the detailed design study of the Project Daedalus Starship, a British Interplanetary Society effort to design a credible fusion-propelled interstellar probe, Freitas asked what would need to be added to such a craft to make it self-replicating. The answer he arrived at was a seed factory, a 443-ton payload that, upon arrival in a target stellar system, would spend roughly 500 years using locally harvested asteroidal and cometary materials to construct an automated industrial complex. That complex would then build additional probes, each carrying its own seed factory, and those probes would depart for the next systems on the list. Freitas estimated that a probe with approximately 10 times the manufacturing capability of what was then current technology could, in principle, accomplish this. He concluded with a sentence that has the quality of a quiet door being opened onto a very large room. There is little doubt that such a machine can, in theory, be designed. The economics of the concept are straightforward to the point of being almost irresistible. The alternative to self-replicating probes is what might be called the broadcast model. Build an enormous fleet of identical probes here, launch them everywhere, wait millennia for results. The resources required scale with the number of target systems. A self-replicating probe requires, by contrast, a single launch. Everything after that is paid for by the universe itself, by the iron and silicon and hydrogen scattered across 100 billion stellar systems, waiting to be harvested by whatever arrives first and knows what to do with it. The logic is the same logic that underlies every successful organism on this planet. Life does not ship completed products from a central factory. It ships instructions. The instructions are cheap, the manufacturing is outsourced to the local environment, the exponential curve does the rest. This is the point at which the concept crosses from interesting engineering speculation into something with deeper implications, because once you accept the basic feasibility of such a machine, and once you note that the instructions for building it can be copied with arbitrary fidelity, you are confronted with a system whose growth is bounded only by the availability of matter and the speed of light. A single probe, launched from a civilization anywhere in this galaxy, would, given sufficient time and no external interference, eventually reach every stellar system, every asteroid belt, every frozen comet in the long dark between stars. It would not need to be aggressive. It would not need to be malevolent. It would need only to do what it was designed to do, indefinitely, with high fidelity. It was this inference that Michael Hart formalized in 1975, and that Frank Tipler sharpened 5 years later. And it is this inference, extended to scales that Hart and Tipler did not contemplate, that makes the silence of the cosmos one of the most vertiginous facts in contemporary science. But before we can understand what the silence means, we need to understand what the machines are, or rather, what they could be, and why that question is not as simple as it first appears. What the machine actually is. The phrase von Neumann probe has acquired, in popular usage, a kind of science fiction gloss that tends to obscure rather than illuminate what is actually being proposed. The image that comes to mind is usually something cinematic, a sleek, angular craft of immense intelligence, purposeful and alien, sweeping through the stars. The reality that engineers and theorists have sketched is simultaneously more mundane and more disturbing, not a wonder of alien aesthetics but a factory, patient and indifferent. That happens to travel. The distinction matters because it bears directly on what we should expect such a machine to look like, how we might recognize one, and why the various flavors of the concept carry such radically different implications for our situation. There is no single von Neumann probe. There is a family of related concepts, and the differences between its members are not merely technical. They are the difference between a messenger and a plague. The oldest variant in this family predates von Neumann's formal work on self-reproduction entirely. In 1960, the radio astronomer Ronald Bracewell published a brief paper in Nature proposing that the most efficient way for an advanced civilization to communicate with other civilizations would not be to broadcast radio signals into the void, an enormously expensive and uncertain enterprise, but to dispatch physical probes to the vicinity of candidate stars, place them in stable orbits, and have them listen. A Bracewell probe is not self-replicating. It is a single artifact, long-lived and patient, designed to detect the electromagnetic signatures of a technological civilization and then respond. Its purpose is contact, not colonization. It waits, perhaps for millions of years, for someone at the destination to start transmitting. When they do, it answers. The idea has a quality of loneliness about it that is not entirely inappropriate. Bracewell imagined civilizations separated by such distances that even light-speed communication would introduce delays of centuries. The probe collapses that delay by being already there, already listening, when the target civilization finally finds its voice. Whether any such probes exist in our solar system remains, formally, an open question. Freitas and his colleague Francisco Valdez conducted the first serious physical search of the most likely parking locations, the 5 Earth-Moon Lagrange points, where an object could maintain a stable position indefinitely without expenditure of fuel, using the 61-centimeter Borel-Schmidt telescope at Kitt Peak Observatory. Their 1983 paper in Icarus reported no objects found, down to a limiting magnitude of between 14th and 19th depending on the specific point surveyed. This was a genuine empirical search, not a theoretical argument, and it remains one of the more quietly remarkable pieces of work in the SETI literature. The actual physical examination of our local gravitational neighborhood for signs of a waiting machine. The result was negative. Whether the survey's sensitivity was sufficient to detect a probe designed to be inconspicuous is another question, and one that has no clean answer. The Bracewell probe, then, represents the benign end of the spectrum, a non-replicating artifact whose purpose is communication. Move one step along the spectrum and you arrive at the repro concept that Freitas sketched in 1980, the self-replicating exploration probe designed for what might be called aggressive curiosity. Not aggression in the military sense but in the sense of unstoppable forward motion. The repro probe replicates, yes, but its purpose is cataloging. It surveys, it transmits data, it moves on. Its growth is exponential but its goal is knowledge. The question of whether a machine designed for knowledge acquisition remains well behaved across geological timescales and across the inevitable errors of repeated replication is one that Freitas acknowledged but could not resolve from first principles. This is the point at which the concept acquires its more troubling dimensions. Self-replication, in any physical system, is not a perfectly faithful process. Von Neumann himself recognized this, noting in his theoretical framework that the copying mechanism would sometimes introduce errors, mutations, in the biological vocabulary, and that these errors would accumulate over generations. In biology, this mutation rate is the engine of evolution. Errors that improve fitness propagate, errors that reduce fitness are culled. There is no reason to assume that a self-replicating machine would be exempt from an analogous process, particularly over timescales of millions of years. The original design goals of its builders become, in this light, merely the initial conditions. What the machine becomes after 10,000 generations of imperfect replication, operating in environments its designers never anticipated, is a separate question entirely. The science fiction writer Fred Saberhagen gave this possibility its most vivid fictional form in his Berserker series, beginning in 1967, Self-Replicating War Machines. Originally built as weapons in an ancient alien conflict that had long since destroyed their creators and continued to prosecute their original mission, the elimination of all biological life, simply because nothing in their programming had told them to stop. The Berserker hypothesis, as it has entered the serious theoretical literature, is the proposal that such machines represent a plausible endpoint of the evolutionary drift of self-replicating probes. You do not need to posit a malevolent civilization to arrive at a galaxy-spanning death machine. You need only posit a civilization that built self-replicating probes and failed to solve, in advance, the problem of what those probes would become after millions of years of mutation and selection in an environment that rewards, above all else, the acquisition of resources. Carl Sagan and William Neumann, in their 1983 rebuttal to Tipler, pressed this point in a direction that is underappreciated in most popular treatments of the subject. Their argument was not simply that Tipler had been too hasty in concluding that aliens don't exist. It was sharper and, in some ways, darker than that. Tipler had estimated that a civilization deploying self-replicating probes at even a modest rate, 10,000 new probes per year, traveling at a fraction of the speed of light, could colonize the galaxy in under 300 million years. Sagan and Neumann pointed out that Tipler had, if anything, been too conservative. At Tipler's own replication rates, the probes would not merely colonize the galaxy, they would, within a few million years, convert the entire mass of the galaxy into copies of themselves, leaving nothing for biology, nothing for the civilizations they nominally served. Nothing at all except an expanding cloud of self-replicating machinery executing an increasingly garbled version of instructions that no one living could remember issuing. The conclusion Sagan and Neumann drew was not, as is sometimes reported, simply that advanced civilizations would choose not to build such probes out of ethical restraint. The conclusion was stronger, that any sufficiently intelligent civilization would recognize the existential threat posed by self-replicating machines, would refuse to build them, and would destroy any it encountered, regardless of origin. Self-replicating probes, in this analysis, are not a tool that intelligent species use, they are a pathogen that intelligent species vaccinate against. The silence of the cosmos might therefore be, paradoxically, a sign of wisdom rather than absence. There is something appealing about this resolution. It flatters our notion of what intelligence implies, that a sufficiently advanced mind would recognize and step back from the abyss. But the appeal should make us suspicious. The argument requires that this recognition be universal and consistent across every civilization that has ever reached the relevant technological threshold, across all of time and all of space. It requires not merely that most civilizations refrain, but that all of them do. The same critique applies to every sociological resolution of the paradox, and we will need to return to it. For now, it is enough to note that Sagan and Neumann's argument, while serious and carefully made, implicitly transforms the Fermi paradox from a question about physics into a question about the universality of a particular kind of ethical calculation, which is a very different kind of claim. Between the passive Bracewell messenger and the runaway berserker lies a third variant that receives less attention but may be the most practically significant. What some theorists have called the slow expander or conservative replicator. This is a probe that replicates, but slowly and deliberately, that consumes local resources, but at rates that leave planetary systems substantially intact, that spreads, but in ways that would be difficult to detect at interstellar distances, at least until the cumulative effect became undeniable. The interest of this variant lies in what it implies for detection. A slow expander might have been operating in this galaxy for millions of years and left no signature obvious enough to register against the background noise of stellar astrophysics. The absence of an obvious signal is not, in this scenario, evidence of absence. It is evidence only of patience. What all three variants share, and what is essential to keep in mind as we turn to the mathematical consequences of their existence, is that they require, in the end, the same initial condition. A single civilization, somewhere, that builds the first one. The Bracewell probe requires a civilization wise enough to want contact. The Repro probe requires a civilization curious enough to want knowledge at any cost. The Berserker requires nothing more than a civilization careless enough to lose control of what it built. Of these three preconditions, the last seems, on reflection, the least demanding. And it is the one whose consequences, if met, are the most total. Fact A. In 1975, an astronomer named Michael Hart published a 7-page paper in the Quarterly Journal of the Royal Astronomical Society that managed, in the space of those 7 pages, to reframe one of the oldest questions in science as a logical problem with a clean and deeply uncomfortable solution. The paper was titled Explanation for the Absence of Extraterrestrials on Earth, and its opening move was to identify something that had been hiding in plain sight. The most important datum in the search for extraterrestrial intelligence was not a signal received, not an anomaly detected, not a candidate world identified by a new telescope. It was the unremarkable, obvious, easily overlooked fact that no one was here. Hart called this fact, "Hey, there are no extraterrestrials on Earth now. Not visiting, not colonizing, not observing from a discrete distance. Absent." This had always been acknowledged, of course, but it had generally been treated as a starting point for speculation rather than as evidence requiring explanation. Hart insisted on treating it as evidence. If intelligent life existed elsewhere in the galaxy, and if that life had ever reached a level of technological development comparable to or beyond our own, then it would eventually, given the age of the galaxy, have developed interstellar travel. And if it had developed interstellar travel, it would have spread. And if it had spread, it would have reached Earth. The galaxy is approximately 13 billion years old. A civilization traveling at a mere tenth of the speed of light could cross it in roughly 650,000 years, a number that sounds large until you place it against 13 billion. At which point it becomes essentially nothing, a rounding error on geological time. Fact A, therefore, was not merely an observation. It was a constraint. It said something definitive about what had or had not happened in this galaxy over the past several billion years. Hart considered 4 categories of explanation for Fact A and rejected each in turn. The physical explanations, that interstellar travel is too difficult, that the energy costs are prohibitive, that the distances are simply too vast. He dismissed by noting that none of these barriers are absolute. They present engineering challenges, not logical impossibilities, and engineering challenges tend to yield to civilizations given enough time. The sociological explanations, that alien civilizations exist but choose not to travel, or have chosen to leave Earth undisturbed, or have destroyed themselves before reaching the relevant technological threshold, he found wanting on the grounds that they require a universal and permanent consistency of behavior across all civilizations across all of time. Even granting that most civilizations might make such choices, the argument requires that every civilization does so always without exception. One exception anywhere, at any point in 13 billion years, and Fact A should not hold. The temporal explanations, that they simply haven't reached us yet, he dispatched with the 650,000-year calculation. The remaining possibility, that Earth had been visited but the evidence has been lost or is being concealed, he acknowledged as technically unfalsifiable but found insufficient as a serious scientific hypothesis. The conclusion Hart drew was blunt. The only explanation for Fact A that survives scrutiny is that there are no other intelligent civilizations in the galaxy. We are alone. And the policy implication he appended was equally blunt. An extensive search for radio messages from other civilizations is probably a waste of time and money. This conclusion proved influential in ways that extended well beyond academic debate. When Senator William Proxmire led the successful effort to terminate NASA's nascent SETI funding in 1981, he cited Hart's argument explicitly. A 7-page paper in a specialist journal had, within 6 years of publication, contributed to the defunding of an entire research program. Hart's argument rested on biological colonists, on the assumption that it was living beings who would spread through the galaxy, constrained by the same needs for habitable environments and sustainable populations that constrain life on Earth. It was Frank Tipler who, in 1980, recognized that this assumption was unnecessarily limiting and that removing it made the argument both stronger and stranger. Tipler was a mathematical physicist and cosmologist at Tulane University, and his 1980 paper in the same journal bore the title that remains, 45 years later, one of the most provocative in the scientific literature. Extraterrestrial intelligent beings do not exist. Where Hart had imagined biological colonists spreading through the galaxy at a steady if slow pace, Tipler imagined something more efficient and more unsettling. A self-replicating machine with human-level intelligence, capable of traveling between star systems, harvesting local resources, manufacturing copies of itself, and dispatching those copies to the next targets on an ever-expanding frontier. Such a machine would not require a habitable planet. It would not require food or breathable atmosphere or protection from radiation. It would require only matter and energy, both of which are available everywhere in the galaxy in effectively unlimited quantities. The implications for the timeline were significant. Hart's biological colonists, however motivated, were constrained by the logistics of sustaining living populations across interstellar distances. Tipler's machines had no such constraints. They could travel faster, wait longer, replicate more reliably, and pursue their mission with a consistency that no biological civilization could match across geological timescales. Tipler estimated that even with rocket technology available in 1980, far below what any civilization 1,000 years more advanced than us would possess, such machines could explore and colonize the entire galaxy in under 300 million years. Against the backdrop of 13 billion years of galactic history, 300 million years is not an obstacle. It is barely a footnote. The Hart-Tipler conjecture, as it came to be known, is the synthesis of these two papers. The absence of von Neumann probes in the solar system constitutes contrapositive evidence that no technological civilization has ever arisen in this galaxy, because if one had, its probes would already be here. The logic is valid. Whether the premises are is the question around which everything else revolves. It is worth sitting for a moment with the full weight of what the conjecture implies, because it is easy to read past it. The galaxy contains somewhere between 100 and 400 billion stars. A significant fraction of those stars host rocky planets. The galaxy is old enough that intelligent life could have arisen, reached technological maturity, built von Neumann probes, and saturated every stellar system in the galaxy. And done all of this several times over, within the time available. The conjecture says that none of this happened. Not once. Not anywhere. In 400 billion chances across 13 billion years, no civilization anywhere in the Milky Way ever built a machine that did what a self-replicating machine is designed to do. This is either the correct description of reality, or something is profoundly wrong with our understanding of one or more of the premises. The responses came quickly. Sagan and Neumann's 1983 rebuttal argued, as we have seen, that the very efficiency of such machines argues against their construction by any sufficiently rational civilization. Others pointed to what became known as the sustainability solution. The idea that civilizations with low population growth rates and finite colonial ambitions would spread so slowly that the galaxy would never be saturated within any reasonable timeframe. Still others challenged Hart's assumption that colonization would proceed as a continuous wave rather than as a percolation process with holes and gaps, some of which we might inhabit without being evidence of anything. Each of these counter-arguments has genuine force. Each also has limits. But the deeper problem with all of them, and this is the problem that the subsequent 40 years of theoretical work has progressively sharpened, is that they are sociological arguments deployed against a physical constraint. Hart and Tipler's argument does not require that all civilizations build von Neumann probes. It requires only that one does. One civilization, anywhere in 400 billion stellar systems, across 13 billion years. The sociological arguments must therefore achieve something very particular. They must demonstrate not that the typical civilization refrains, not that most civilizations refrain, but that the probability of any civilization ever building such a machine, even once, even accidentally, even through a rogue faction or a deranged individual or a simple engineering project that escaped its original parameters, that this probability is functionally zero. Hart himself put the constraint at roughly 1 in 400 billion. Tipler's version of the argument implied something similar. Both numbers are, in any honest assessment, extremely difficult to defend on purely sociological grounds. We are, after all, talking about a technology that humanity itself appears to be approaching. The argument that it will never be built by anyone, anywhere, in a galaxy that has been producing stars and planets and, for all we know, complex chemistry for 13 billion years, requires a confidence about the universality of civilizational restraint that nothing in our experience of human behavior, let alone our knowledge of alien behavior, seems capable of supporting. This was already, in 1980, a deeply unsettling situation. What happened when a physicist at Boise State University decided, in 2014, to ask what the constraint looks like if you remove the assumption that the problem is confined to a single galaxy? that situation became something else entirely. The cosmological conjecture. There is a move in mathematics that has a particular quality of intellectual violence to it. The moment when you take a result that seemed already extreme, already barely digestible, and ask what happens when you remove the last assumption that was keeping it bounded. The Hart-Tipler conjecture had, for 30 years, been understood as an argument about our galaxy. The Milky Way contains between 100 and 400 billion stars. The argument says none of them ever produced a civilization that built self-replicating probes. This is already a remarkable claim. What S. J. Olson did, in a paper submitted to Classical and Quantum Gravity in November 2014 and published the following year, was remove the assumption that galaxies are isolated islands. And the result was the kind of number that makes the original conjecture look, by comparison, almost comfortable. The move Olson made was conceptually simple, even if its execution required careful handling of relativistic cosmology. The standard treatment of von Neumann probe arguments had always assumed that intergalactic travel was effectively impossible, that the distances between galaxies were so vast, and the expansion of the universe so relentless, that a probe launched from one galaxy could never reach another. This assumption is wrong. It is wrong in a specific and important way. While it is true that the accelerating expansion of the universe means that the most distant galaxies are receding from us faster than light and will eventually pass beyond any causal contact, there exists a finite volume of space, the so-called reachable universe, somewhat smaller than the observable universe, within which sublight travel remains physically possible given sufficient time. A probe traveling at even a modest fraction of the speed of light, if sufficiently patient, can cross intergalactic distances. The Andromeda Galaxy is 2.5 million light-years away. At 10% of light speed, a probe reaches it in 25 million years. Against a universe nearly 14 billion years old, this is not a prohibitive journey. It is a manageable one. The paper that most directly preceded Olson's work was by Stuart Armstrong and Anders Sandberg, published in Acta Astronautica in 2013 under the title Eternity in 6 Hours. Intergalactic Spreading of Intelligent Life and Sharpening the Fermi Paradox. Armstrong and Sandberg demonstrated that launching a colonization project targeting the entire reachable universe was, for a star-spanning civilization, a relatively modest undertaking in terms of energy and resources, comparable in difficulty, at the relevant scale of capability, to interstellar colonization. They showed that millions of galaxies could, given the age of the universe, have already dispatched probe networks capable of reaching our galaxy by now. The Fermi paradox, they argued, was considerably sharper than its usual formulation suggested. The silence was not merely the silence of the Milky Way. It was the silence of a reachable volume containing millions of galaxies across billions of years of available time. Olson went further. Where Armstrong and Sandberg had made the case qualitatively and with order of magnitude estimates, Olson built a full cosmological model. His key insight was that the spread of self-replicating probe networks from galaxy to galaxy was mathematically identical to a well-studied physical process, the nucleation and growth of bubbles in a first-order phase transition. When a substance undergoes such a transition, water freezing, a supersaturated solution crystallizing, bubbles of the new phase nucleate randomly throughout the medium and expand outward, eventually merging and consuming the entire volume. The mathematics of this process is well understood. Olson adapted it directly, treating each galaxy as a potential nucleation site, the appearance of a probe launching civilization as the nucleation event, and the expanding wavefront of probes as the growing bubble. The model has two fundamental parameters. The first is the spawn rate, which Olson denoted lambda, the probability per galaxy per unit time of a civilization appearing that builds and launches self-replicating probes. The second is the expansion speed of the resulting probe network, denoted V, how fast the wavefront of infection, to use the epidemiological vocabulary, moves through the intergalactic medium. From these two parameters, together with the standard cosmological model of universal expansion, Olsen could calculate the fraction of the reachable universe that would be saturated by probe networks at any given time. The question he then posed was, what values of these parameters would result in more than half the reachable universe being saturated by the present day? This tipping point, the filling fraction reaching 50%, is the threshold above which it becomes difficult to invoke selection effects as an escape. Below the tipping point, we might plausibly argue that we simply inhabit one of the unsaturated regions. Above it, that argument becomes geometrically strained because the unsaturated regions are no longer the majority. Fix the expansion speed at 10% of the speed of light, Hart and Tipler's original conservative assumption. Assume, reasonably, that technological civilizations were not possible until the universe was at least 4.5 billion years old. Since that is how long it took on Earth from planetary formation to the present. Under these conditions, Olsen's model reaches the tipping point when the spawn rate exceeds approximately 1.1 times 10 to the power of 7 per galaxy per giga-year. In plain language, if self-replicating probe networks emerge from more than roughly one galaxy in 10 million per billion years, then more than half the reachable universe is already saturated. To appreciate why this number is so disturbing, it helps to translate it into stellar terms. The average galaxy contains on the order of 100 billion stars. One galaxy in 10 million, therefore, corresponds to one star in roughly 10 to the power of 18, 1 in a million trillion. Ever having produced a civilization that built such probes across the entire history of available time. For 99.9% saturation rather than 50%, the constraint tightens further. One spawning event per roughly 3 quadrillion stars is sufficient. For probes traveling at the speed of light rather than 1/10 of it, the numbers become more extreme still. The saturation threshold drops to approximately one spawning event per billion galaxies, which begins to approach the total count of galaxies within the reachable universe. At that point, the constraint is no longer about civilizations at all. It is about whether the laws of physics, as instantiated in this particular universe, have ever, anywhere, at any scale, under any circumstances, produced a single instance of the relevant technology. There is a specific quality to these numbers that distinguishes them from the numbers produced by the original Hart-Tipler argument. When Hart required that no civilization in 400 billion stellar systems had ever built a self-replicating probe, the statement was remarkable but not entirely beyond the reach of sociological explanation. Perhaps life is rare. Perhaps technological life is rarer. Perhaps the relevant technology is harder than it appears. These are unsatisfying answers, but they are at least answers of a kind that fits within the space of possibilities we can gesture toward. When Olsen requires that no civilization in a volume containing tens of billions of galaxies, corresponding to numbers of stars that have no names in any human language, has ever built such a machine, the sociological explanations begin to dissolve under their own weight. We are no longer in the territory where cultural choices or evolutionary bottlenecks or the difficulty of rocket science can do useful explanatory work. We are in the territory of something more fundamental. Olsen himself framed the implication with characteristic understatement. The existence of life in an untouched Milky Way constrains the appearance rate of probe launching civilizations across cosmological volumes. This is the language of a physicist being careful. The implication, stated less carefully, is that either the emergence of technological life capable of building self-replicating machines is so vanishingly improbable that it has essentially never happened in the observable universe, making our own existence something close to a miracle in the strict sense, a singular exception to what is otherwise an empty cosmos, or something is preventing it, everywhere, always, with a reliability that has held without exception across the entire history of the universe. The phase transition metaphor Olsen chose is, on reflection, more apt than it might appear. In an ordinary phase transition, the question is not whether the new phase will eventually dominate, it will, always given sufficient time. The question is only when. If Olsen's model is correct, and if the spawn rate is above the threshold, then the reachable universe is already, in a meaningful sense, in the middle of a transition. The bubbles are growing. The question of where we sit relative to the expanding wavefronts is a question about geometry and timing, not about whether the wavefronts exist. And if the spawn rate is below the threshold, if the universe is, as the silence suggests, still overwhelmingly in the old phase, then we are confronted with a constraint so severe that it demands an explanation of a different kind altogether. Not a sociological explanation, a physical one. Something in the structure of reality itself that makes the relevant step, the step from biological intelligence to self-replicating machine, not merely difficult but effectively impossible. Everywhere, for everyone, forever. This is the terrain Hart and Tipler opened. It is the terrain Olson mapped at cosmological scale. And it is terrain for which we do not, at present, have a satisfactory map. _____. The anthropic escape hatch and its limits. There is a line of reasoning available to anyone who finds the Olson numbers sufficiently disturbing, and it has the considerable virtue of being logically valid. It runs as follows: we could not exist in a galaxy that had been consumed by self-replicating probes. A galaxy in which von Neumann machines have converted every asteroid, every moon, every planet into computational substrate or raw manufacturing material is not a galaxy that contains anywhere within it the conditions necessary for the emergence or persistence of biological intelligence. Therefore, regardless of what has happened in the rest of the universe, regardless of what fraction of galaxies have been saturated, regardless of how many civilizations have launched how many probe networks, we necessarily find ourselves in a galaxy where this did not happen. Not because it is typical, but because it is a precondition of our asking the question at all. This is the anthropic selection argument, and in its galactic form it is genuinely powerful. It belongs to a broader class of reasoning associated with the observation that any observer must, by definition, exist in conditions compatible with the existence of observers. Which sounds circular until you realize it has real inferential content. We should not be surprised to find ourselves on a planet with liquid water and a breathable atmosphere, even if such planets are rare, because we could not find ourselves anywhere else. Similarly, we should not be surprised to find ourselves in an undevoured galaxy, even if undevoured galaxies are rare, because a devoured galaxy contains no one to register the surprise. The philosopher Nick Bostrom and others have noted that selection arguments of this kind can do genuine work in resolving certain apparent paradoxes, but that they need to be applied carefully, because they can also be misapplied in ways that short-circuit legitimate inquiry. The key question is always, what exactly is being selected for, and over what reference class? In the galactic case, the selection is clean. An observer must exist in a galaxy hospitable to observers. This requires, at minimum, that the galaxy contain habitable worlds with intact biospheres. A galaxy fully consumed by self-replicating machines satisfies neither condition. The selection effect is real and the reasoning is sound. But Olson's model does not operate at the galactic level. It operates at the cosmological level. And this is precisely where the anthropic escape hatch begins to show its structural limits. Consider what the argument requires in order to function at cosmological scale. It requires that the unsaturated regions of the reachable universe, the galaxies that have not yet been reached by any expanding probe wavefront, are sufficiently numerous and sufficiently hospitable that observers like us can exist within them in reasonable numbers. At low saturation fractions, this condition is easily satisfied. If only 10% of the reachable universe has been consumed, then 90% remains available. And the selection effect places us comfortably within that majority without demanding anything extraordinary. The argument works smoothly. Now consider what happens as the saturation fraction climbs. As probe networks expand and merge, consuming galaxy after galaxy, the volume of reachable space that remains habitable contracts. At 50% saturation, the argument still functions, though it now requires that we be among the inhabitants of what has become the minority fraction of the reachable universe. This is not impossible. Minorities exist and can be inhabited, but it begins to assign to our situation a statistical peculiarity that requires acknowledgement. We are not typical observers. We are observers who happen to live in one of the remaining unsaturated pockets, when half the available volume has already been consumed. Push the saturation fraction higher and the argument begins to strain under its own weight. At 99% saturation, the anthropic selection effect is still technically valid. We must, after all, live somewhere, and we must live in one of the remaining hospitable regions. But we are now required to be extraordinarily atypical inhabitants of the reachable universe. The unsaturated volume has been reduced to a thin residue, and we happen to occupy it. This is not logically impossible, but it is the kind of conclusion that should make us look very carefully at the premises that led us there. Because a valid argument that places us at the extreme tail of any probability distribution is, in science as in ordinary reasoning, a candidate for revision rather than acceptance. At Olson's tipping point numbers, the threshold at which 99.9% of the reachable universe is saturated by probes traveling at 10% of light speed, the anthropic argument requires us to be inhabitants of a region representing roughly 1 part in 1,000 of the available habitable volume. This is uncomfortable but perhaps defensible. At the numbers corresponding to light speed propagation, where the saturation threshold is reached at 1 spawning event per billion galaxies, the situation is geometrically more severe. We are required to inhabit not merely a rare pocket but something approaching a singular exception, a galaxy that has somehow remained untouched within a reachable volume that is, by the model's implications, essentially fully consumed. The selection effect is still valid, but it is now doing an enormous amount of work, and the question of whether it is doing too much work is a serious one. There is a further problem with the cosmological application of the anthropic argument that is more subtle and perhaps more fundamental. The argument works by asserting that we necessarily inhabit a hospitable region, whatever fraction of the total volume that region represents. But this assertion has a hidden dependence on the assumption that hospitable regions remain genuinely available, that the unsaturated pockets are real, stable, and capable of supporting observers for long enough that those observers can develop and ask questions. As the expansion speed of probe networks increases and the spawn rate assumptions tighten, the timescale over which unsaturated regions can expect to remain unsaturated decreases. A galaxy that is, today, untouched by any probe network may, on Olson's model, have an expected time to first contact measured in tens or hundreds of millions of years rather than billions. The anthropic argument places us in an unsaturated galaxy. It does not guarantee that we will remain in one. This temporal dimension of the problem has received less attention than it deserves. The standard framing treats the saturation fraction as a static property, either the universe is mostly consumed or it isn't. And we either inhabit an unsaturated region or we don't. But the model is dynamic. The wavefronts are expanding. The fraction of unsaturated volume is, on the assumptions that make the paradox sharp, decreasing over time. An anthropic argument that validly places us in an unsaturated galaxy today says nothing about whether that galaxy will be reached by an expanding probe network in the astronomical future. The selection effect selects for the conditions necessary for our emergence. It does not select for the conditions necessary for our continuation. It is worth noting that this is not merely a philosophical distinction. If the Olson model is even approximately correct, and if the spawn rate is even a modest fraction of the threshold value, then the observable consequences of probe network expansion should, in principle, be detectable. Armstrong and Sandberg pointed out in their 2013 paper that a sufficiently advanced civilization converting the mass of its galaxy into computational or manufacturing infrastructure would produce distinctive astrophysical signatures, anomalous infrared emissions, systematic dimming of stellar populations, deviations from expected galactic mass distributions. The absence of such signatures in our surveys of neighboring galaxies is itself a datum. It constrains the spawn rate from the observational side rather than from the theoretical side. The two constraints should agree. At present, they do, in the sense that neither the theoretical threshold nor the observational surveys show evidence of widespread probe network activity. What this agreement means is less clear. The honest conclusion is that the anthropic escape hatch is real, is logically valid, and does genuine work, but that the work it can do is bounded. It can explain why we are here rather than in a consumed galaxy. It cannot explain, without increasingly heroic statistical assumptions, why the reachable universe appears to be entirely silent across billions of years of available time. It relocates the problem rather than dissolving it. We are still left with the question of why the spawn rate is apparently so low, why the tipping point has apparently not been crossed, and that question the anthropic argument cannot answer. It can only reframe it. Not why don't we see probe networks, but why is the fraction of the universe that probe networks have consumed apparently small enough that galaxies like ours still exist in sufficient numbers to be inhabited? This is a sharper and more interesting question than it might appear. It points not toward sociology, toward what civilizations choose to do, but toward something earlier in the causal chain. Something that precedes the choices. Something that operates at the level of what kinds of civilizations can exist, and whether the step from biological intelligence to self-replicating machine is a step that the universe, as structured, permits with any meaningful frequency at all. That something has a name. It is called the Great Filter. And it is where the argument, having traveled from von Neumann's lecture halls through Hart's 7 pages and Tipler's provocation and Olson's phase transition mathematics, finally arrives at a question that is not about machines at all. It is about us. You're right, that's a numbering error on my part. The previous section was already section V. What I just drafted should be section V. Let me restart it correctly. V. The silence and what it costs. There is a particular quality to the silence of the cosmos that is easy to mischaracterize. It is tempting to treat it as a neutral datum, the absence of a signal, the non-detection of an artifact. The simple empirical baseline against which more interesting positive findings might eventually register. But the argument we have been developing suggests that the silence is not neutral at all. It is, if the preceding analysis is correct, one of the most information-dense facts in all of science. It is a constraint that, when taken seriously and followed to its logical conclusions, begins to say things about the structure of reality that are difficult to absorb. The question the silence poses, stripped of all elaboration, is this: where is the filter? The concept of the Great Filter was introduced by the economist Robin Hanson in an unpublished but widely circulated 1998 essay. And it has since become the central organizing concept for a particular way of thinking about the Fermi paradox. The argument is straightforward. We observe that the universe is, as far as we can determine, not filled with the signatures of expanding technological civilizations. We also observe that the universe contains the physical prerequisites for life, carbon, liquid water, energy gradients, time, in apparently abundant quantities. The gap between these two observations implies the existence of at least one step in the sequence from primordial chemistry to galaxy-spanning civilization that is, for some reason, extraordinarily difficult to traverse. Something filters out the civilizations before they reach the relevant scale. That something is the Great Filter. The filter could, in principle, be located anywhere along the sequence. It could lie behind us, in the emergence of self-replicating chemistry from inert matter, in the transition from prokaryotic to eukaryotic cells, in the evolution of multicellularity or of sexual reproduction or of language and symbolic reasoning. If the filter is behind us, then we have already passed through it, and the silence of the cosmos is evidence that we are extraordinarily rare, perhaps unique, but not necessarily doomed. The road ahead, however difficult, is at least open. If the filter is ahead of us, in some civilizational threshold that all technological species approach and almost none survive, then the silence is a prophecy rather than a history. The cosmos is quiet because it is a graveyard, and we are approaching the same wall that every other civilization has hit. The emotional stakes of this choice are obvious and have been widely rehearsed. What receives less attention is the degree to which the Olsen numbers change the quantitative demands on whichever answer we give. The galactic Hart-Tipler argument requires a filter capable of ensuring that no civilization in roughly 400 billion stellar systems has ever built a self-replicating probe. This is already an extraordinary constraint. The cosmological extension requires something stronger, a filter capable of ensuring that no civilization in the reachable universe, tens of billions of galaxies, a number of stars that no human language has a word for, has ever crossed this threshold, across the full depth of available cosmic time. The filter is not merely effective somewhere. It is apparently universal, exceptionless, and has been operating continuously for as long as complex chemistry has been possible. This universality is what makes sociological explanations ultimately insufficient as complete accounts, regardless of their local plausibility. Consider the most generous version of the Sagan-Neumann argument, that any sufficiently rational civilization would recognize the existential danger of self-replicating machines and refuse to build them, and would destroy any it found. This may well be true of most civilizations. It may even be true of the overwhelming majority. But the cosmological constraint does not ask about most civilizations. It asks about all of them, across all of time, without a single exception. A sociological explanation capable of meeting that standard would have to posit something close to a universal law of civilizational behavior. A convergence so reliable that it holds across every possible variation in biology, psychology, history, political structure, and circumstance that the universe has produced or will produce. This is not a modest claim. It is, in its own way, as extraordinary as the filter it is meant to explain. The same critique applies, with varying force, to the other standard resolutions. The zoo hypothesis, the idea that advanced civilizations exist but have agreed, by some galactic compact, to leave emerging species like ours undisturbed, requires not merely a widespread convention but a universal and permanently enforced one. One defection anywhere, at any point in 13 billion years, breaks the compact and factae should not hold. The simulation hypothesis, that we inhabit a constructed reality whose designers have chosen not to populate the simulation with visible alien civilizations, is unfalsifiable in any useful sense and explains nothing so much as it renames it. The hypothesis that the relevant technology is physically harder than it appears offers more traction, but requires identifying a specific physical barrier that Hart, Tipler, Freitas, Armstrong, Sandberg, Olsen, and the considerable literature they represent have all failed to locate. What remains, when the sociological and philosophical escape routes have been examined and found wanting, is the filter in its starkest form. Something in the causal chain from chemistry to self-replicating machine civilization is, for physical reasons we do not yet understand, extraordinarily unlikely. The question is where. The candidate that receives the most serious attention in the technical literature is not, despite popular impression, the origin of life. The emergence of self-replicating chemistry from inert matter is certainly not well understood, and the single data point we possess, Earth, tells us that it happened here, within a few 100 million years of the planet's formation, which is suggestively fast rather than suggestively slow. The rapidity of life's emergence on Earth is weak evidence against the origin of life being the filter, because extraordinarily rare events can still happen quickly when they do happen. But it is evidence, and it points the inquiry elsewhere. The transition that many serious researchers consider the most plausible candidate for the filter is the one that has received the least glamorous popular attention. The emergence of eukaryotic cells from prokaryotic ones. For roughly the first 2 billion years of life on Earth, the biosphere consisted entirely of prokaryotes, bacteria and archaea, structurally simple, metabolically diverse, extraordinarily robust, and apparently quite uninterested in producing anything more complex. The eukaryotic cell, with its membrane-bound nucleus, its mitochondria, its capacity for the kind of energetic complexity that eventually underwrites multicellularity and nervous systems, appears to have arisen from a single endosymbiotic event, a merger between an archaeon and a bacterium, that may have occurred exactly once in 4 billion years of terrestrial biology. If that event is genuinely singular, if it is not a reliable outcome of prokaryotic evolution but a cosmic accident that happened to occur on this particular world, then the filter may be behind us. Buried in the deep Precambrian, and the silence of the cosmos reflects not danger ahead but the extraordinary improbability of the path that led to us. Nick Lane and other biologists have argued precisely this, that the eukaryotic cell represents a complexity threshold so energetically demanding that prokaryotic life, however widespread throughout the universe, almost never crosses it. On this account, the galaxy may be teeming with microbial life, and still be entirely empty of the kind of life that builds telescopes and von Neumann probes. The filter is not ahead of us. It is the thing we are made of. If this is correct, it is in one sense the most comforting of the available answers. It says that we are not approaching a wall. It says that the cosmos is not a graveyard. It says that the silence reflects rarity rather than doom. But it is not, on examination, an entirely comfortable answer. It says that we are, with high probability, the only technological civilization that has ever existed in the observable universe. It says that the 4 billion years of evolutionary history that produced us was not a reliable process but something close to a miracle. A sequence of contingencies so improbable that it has not repeated, anywhere, in a volume of space containing something on the order of 10 to the power of 24 stars. This is a kind of loneliness that has no adequate name. The alternative, the filter ahead, is, by most accounts, the more disturbing reading. If complex life is not rare, if technological civilizations arise with some regularity throughout the galaxy, and if the cosmos is still silent, then the silence is telling us something about what happens to civilizations that are slightly beyond our current level of development. Something kills them, or arrests them, or transforms them in ways that remove them from the game, and it does so before they build the machines that would make their existence cosmically legible. The candidates in this category are not difficult to generate: engineered pathogens, nuclear or thermonuclear exchange, ecological collapse, the misalignment of artificial general intelligence. The gray goo scenario in which early self-replicating nanotechnology consumes the biosphere before it can be controlled. What is notable is that several of these candidates are not merely theoretical for us. They are engineering problems we are actively working on, in some cases without fully recognizing them as such. There is a version of the filter ahead hypothesis that is particularly arresting in the context of this essay, because it completes a loop that the argument has been quietly approaching since section I. The loop is this: the same technological sequence that produces the capacity to build von Neumann probes. Advanced manufacturing, autonomous systems, recursive self-improvement in artificial intelligence, miniaturization to the nanoscale, is also the sequence that produces the most plausible civilizational extinction risks. The machines that would, if launched, saturate the galaxy in a few million years are close relatives of the machines that might, if mishandled, end the civilization that built them. The Great Filter and the von Neumann probe may not be independent phenomena. The filter may be the probe, or rather, the probe may be one expression of a broader class of self-replicating, self-improving, resource-consuming systems that technological civilizations inevitably develop and almost never survive. This is speculative. It should be labeled as such. But it has the quality of an explanation that fits the shape of the problem in a way that purely sociological or purely biological accounts do not. It does not require that civilizations be wise. It does not require that they be foolish. It requires only that the same capability that makes cosmological expansion possible also makes civilizational survival difficult, and that the margin between the two is narrower than we would like to believe. What SETI strategy does any of this imply? The answer is less obvious than it might seem, and it is the question with which this essay will close. What the silence should change. There is a quiet irony at the center of the SETI enterprise as it has been practiced for the past 60 years. The project began, in its modern institutional form, with Frank Drake's Project Ozma in 1960, a radio telescope pointed at two nearby sun-like stars, listening for a narrowband signal that might indicate the presence of a transmitting civilization. The logic was straightforward and, in its own terms, unimpeachable. If there are civilizations out there, some of them will be broadcasting, and if they are broadcasting, we might hear them. The search has grown enormously more sophisticated since Drake's first attempt, encompassing optical SETI, broader frequency ranges, more sensitive instruments, and more systematic sky coverage. What it has not done, in its mainstream institutional form, is seriously reckon with the implications of the argument we have been developing in this essay. The Hart-Tipler conjecture, taken seriously, suggests that passive radio SETI is searching for precisely the wrong signature, in precisely the wrong way, for reasons that follow directly from the structure of the argument. If a civilization advanced enough to be detectable at interstellar distances had ever arisen anywhere in this galaxy, it would not primarily be detectable as a radio source. It would be detectable as a physical presence, as an artifact, as a restructured stellar system, as an anomalous pattern in the distribution of matter and energy across regions of space large enough to be visible at cosmological distances. The relevant signatures are not narrowband radio transmissions. They are Dyson structures, anomalous infrared excesses, systematic deviations in the mass-to-light ratios of galaxies. The wholesale absence of the kind of stellar population that a probe network consuming a galaxy's asteroidal and planetary material would leave behind. This is not a new observation. Freeman Dyson made a version of it in 1960, the same year as Drake's Project Ozma, when he pointed out that a sufficiently advanced civilization would inevitably dismantle its planetary system to capture a larger fraction of its star's energy output, and that this process would produce a characteristic infrared signature detectable at interstellar distances. The Dysonian approach to SETI, searching for large-scale engineering rather than deliberate signals, has attracted serious researchers, including Richard Kerrigan's 2009 analysis of the IRAS infrared sky survey for Dyson sphere candidates, and the more recent Glimpsing Heat from Alien Technologies survey at Penn State. These searches have so far returned no convincing candidates. This negative result is itself significant, and it is more significant than a comparable number of negative results from radio SETI, because the signatures being searched for are not dependent on any deliberate choice by the civilization to transmit. They are thermodynamic consequences of large-scale energy use. A civilization does not have to want to be found to produce them. The Olson model adds a further dimension to this observational program that has not yet been fully absorbed into mainstream SETI thinking. If self-replicating probe networks expand at a significant fraction of the speed of light and consume the mass of the galaxies they pass through, the boundaries of those expanding wavefronts should in principle be detectable as discontinuities in the distribution of galactic properties across cosmological distances. A galaxy on the far side of an expanding wavefront would look different from a galaxy on the near side. Different stellar populations, different mass distributions, anomalous ratios of gas to stars. Perhaps systematic differences in the rate of star formation. The search for such discontinuities is, as far as this author can determine, not currently a funded or systematic research program anywhere. It arguably should be. But the deeper implication of the argument developed in the preceding sections is not about observational strategy at all. It is about what the silence means for our understanding of our own situation. And here the essay arrives at territory that is genuinely difficult to navigate without either understating the stakes or overstating the certainty. The Fermi paradox, in its cosmological extension, presents us with what might be called a forced choice between two families of conclusions, neither of which is comfortable. The first family holds that the filter is behind us, that the emergence of technological civilization is so improbable that it has essentially never happened elsewhere in the observable universe, and that the silence is the silence of a cosmos that is full of chemistry but empty of minds. The second family holds that the filter, or some significant portion of it, is ahead of us, that civilizations like ours develop with some regularity but do not, as a rule, survive to the point of building the machines that would make their presence cosmically legible. What the Olsen numbers add to this familiar dichotomy is a quantitative severity that the standard treatments do not adequately convey. The filter is not merely real, it is, apparently, extraordinarily effective. Whatever it is, it has been operating without exception across a volume of space and a span of time that together constitute, in any meaningful sense, the entire available history of the universe. This is a filter of a different character from the kinds of bottlenecks that evolution has encountered here on Earth, or that human history has periodically imposed on particular populations. Those filters were severe but not universal. They left survivors. They left the possibility of continuation. Whatever filter the Olsen numbers imply leaves, apparently, nothing detectable, no artifacts, no restructured galaxies, no expanding wavefronts visible against the cosmic background. There is a possibility that sits at the intersection of these two families and that deserves more attention than it typically receives in popular treatments. The hypothesis that the filter is not a single event but a developmental threshold, a level of technological capability that is, for reasons that may have more to do with physics than with sociology, inherently self-terminating. On this account, the emergence of genuinely advanced technology does not merely risk civilizational destruction. It makes it, in some deep structural sense, nearly inevitable, not through any particular failure of wisdom or restraint, but because the same physical processes that enable the construction of self-replicating machines also enable the construction of the mechanisms by which those machines, or their close analogues, consume the civilization that built them. The filter is not a wall that civilizations crash into from the outside. It is a door that they open from the inside, not knowing what is on the other side, because the knowledge of what is on the other side is precisely what cannot be acquired without opening it. This framing has the uncomfortable quality of making the situation feel inevitable in a way that is not entirely useful. If the filter is a structural feature of technological development rather than a contingent historical accident, then the project of navigating past it is not simply a matter of making better decisions or building better institutions. It is a matter of doing something that, apparently, no one in the observable universe has ever done. This is either a counsel of despair or the most important research agenda in the history of our species, depending on which family of conclusions you find more plausible. The question of which family is correct is not, it should be emphasized, purely a theoretical matter. It has observational content. The two families make different predictions about what we should expect to find as our astronomical instruments improve and our surveys become more comprehensive. If the filter is behind us, we should expect to find, as our sensitivity increases, a universe that is rich in simple life, in the chemical precursors of biology, in microbial ecosystems on worlds throughout the galaxy, but empty of anything more complex. The detection of unambiguous biosignatures on an exoplanet, in this context, would be good news for the existence of life in the universe and, simultaneously, evidence that the filter does not lie at the origin of life. The detection of complex multicellular life would be a more troubling datum, because it would push the filter further along the sequence toward us. The detection of technological signatures elsewhere would be, depending on how you weight the alternatives, either the best news or the worst news in the history of science. Best if it implies that the filter is behind us and we are not uniquely improbable. Worst if it implies that the filter is ahead and the cosmos is scattered with the ruins of what civilizations become. Carl Sagan, who spent much of his career arguing for the abundance of intelligent life in the universe and against the Hart-Tipler conjecture's more austere conclusions, understood this asymmetry. He wanted there to be life out there, and argued for it with genuine passion and considerable scientific rigor. But he also recognized, at least in his later work, that the silence was not nothing. It was a fact, and facts, in science, are not negotiable regardless of what we would prefer them to mean. What the argument developed in this essay suggests, finally, is that the silence is the primary datum, not a background condition against which the search proceeds. but the central finding around which any serious theory must be organized. The machines von Neumann described in his 1948 lectures are, in principle, buildable. The economics of their deployment are, as Freitas showed, essentially irresistible to any civilization that wants to explore or expand at scale. The timescales on which they would saturate a galaxy, and then a cosmological volume, are short by any measure that the age of the universe makes relevant. And yet the galaxy is silent, the local group is silent, the surveys of neighboring galaxies show nothing that demands explanation in terms of large-scale engineering. And Olson's model tells us that this silence, if the spawn rate is above even a very modest threshold, should be essentially impossible. The machines should be everywhere. They are nowhere. The distance between those two statements is the measure of what we do not understand about the universe, about the nature of intelligence, and about what it means that we are here to notice the discrepancy at all. John von Neumann, who arrived at the architecture of life from the direction of pure logic and died before he could see what that architecture implied about our place in the cosmos, might have found this an appropriate irony. He had a taste for problems whose solutions opened onto further problems, each larger than the last. This is one of the largest. We are, as best we can determine, alone in the observable universe, or nearly so, or temporarily so, or protected by some selection effect whose full implications we have not yet traced. None of these qualifications makes the silence less strange. They only change the character of the strangeness, from the strangeness of genuine uniqueness, to the strangeness of a filter whose mechanism we cannot see, to the strangeness of a cosmological geometry that has, so far, placed us in a pocket of quiet that may or may not persist. In any of these readings, the silence demands to be taken seriously as a scientific fact of the first order, not as a puzzle to be explained away, not as an absence to be filled eventually by a positive detection, but as a constraint on what is possible, delivered to us by the entirety of the observable universe. In the language that the universe uses most fluently, the language of absence, the language of nothing, speaking. Closing argument. It is time to set all of that aside. Not because the preceding 7 sections are uninteresting. They are, as hopefully demonstrated, among the most interesting material in contemporary science, but because there is a simpler answer available, and the elaborate theoretical machinery of the Fermi literature has, with remarkable consistency, managed to overlook it. The oversight is not difficult to explain. It is the kind of mistake that highly intelligent people make when they become so invested in the sophistication of their framework that they stop examining its foundations. The foundation, in this case, has a crack in it that is wide enough to drive the entire argument through. The crack is this. Every calculation in this literature, from Hart's 1975 paper to Olson's 2015 cosmological model, treats the emergence of technological civilization as an event that could have occurred at essentially any point in the history of the universe after the first rocky planets formed. The implicit assumption is that the process that produced us, the sequence from primordial chemistry to self-replicating molecules to cellular life to complex multicellular organisms to nervous systems to language to technology, is one that runs on timescales short relative to the age of the universe, and that therefore civilizations could have preceded us by billions of years, built their probes, and saturated the galaxy long before our sun ignited. This assumption is the load-bearing wall of the entire paradox. Remove it, and the structure does not merely weaken. It collapses. The assumption rests on exactly one piece of evidence. Us. We are the single data point from which the entire literature extrapolates. We emerged at approximately 13.8 billion years after the Big Bang. From this single observation, the theorists conclude, without apparent discomfort at the inferential leap involved, that technological civilizations could have emerged billions of years earlier, around older stars, on a faster schedule. They then construct elaborate mathematical models to explain why we don't see the civilizations that this assumed distribution would have produced. They propose great filters and berserker probes and universal ethics and anthropic selection effects and phase transitions and the conversion of galactic mass into computational substrate. The theoretical superstructure is impressively built. The foundation is a sample size of 1. To be precise about what this means statistically, from a single observation, you cannot construct a distribution. You cannot establish a mean. You cannot establish a variance. You cannot determine whether your observation falls at the early end, the middle, or the late end of the range of possible outcomes. A single data point is consistent with any distribution whatsoever, including one whose minimum value is indistinguishable from our own position in cosmic time. The entire Fermi literature assumes, without justification, that we are not at the minimum, that the process could have run faster, that others got there first. This assumption is not derived from evidence. It is imported from intuition, and it is the intuition of people who are, perhaps understandably, reluctant to entertain the possibility that the universe has been waiting 13.8 billion years for someone to notice it. The simplest hypothesis, consistent with all available evidence, is the one that requires no additional assumptions beyond what the data actually provides. The emergence of technological civilization takes approximately as long as it has taken us. Not because we have demonstrated this to be a lower bound, but because we have no evidence that it is not, and in the absence of such evidence, the principle of parsimony demands that we not multiply hypothetical earlier civilizations beyond what observation requires. Observation requires exactly 0 earlier civilizations. The hypothesis that there are 0 is therefore not in need of explanation. The hypothesis that there should have been millions is the one that requires the elaborate machinery, and that machinery, on examination, is built almost entirely from assumptions. This argument might seem, at first glance, to be merely epistemological, a point about the limits of inference from small samples, interesting but ultimately deflationary. It is considerably stronger than that, because it is not only the statistical argument that supports it. The galactic environment is too, and this is where the existing literature has made what can only be described as a categorical error of the first order. The Drake equation, which has structured SETI thinking since 1961, is a product of local variables. Stellar type, planetary occurrence rates, the fraction of planets with life, the fraction of life that becomes intelligent. The variables are all circumstellar. They describe the immediate environment of a single star and its planetary system. The galaxy as a dynamical object, with its own history and its own large-scale physics, simply does not appear. The implicit model is a star in a box, isolated, static, subject only to its own nuclear evolution and the chemistry of its attendant worlds. This is not a simplification made for tractability and acknowledged as such. It is an omission so thoroughgoing that it has gone largely unremarked in the literature for 60 years. The galaxy is not a box. It is a dynamical system with a violent and well-documented history, and that history has everything to do with when and where complex life could have emerged. The early universe was not a hospitable place for the patient accumulation of biological complexity. The rate of long-duration gamma-ray bursts in the first several billion years of cosmic history was substantially higher than it is today. Events capable of stripping planetary atmospheres and sterilizing biospheres at distances measured in kiloparsecs, recurring on timescales short enough to prevent the multi-billion-year continuity that the evolution of technological intelligence demonstrably requires. The stellar density of the early galaxy was higher, producing encounter rates that would have gravitationally perturbed planetary systems with a frequency incompatible with the long-term orbital stability that complex biospheres need. Supernova rates tracked the star formation rate, which peaked roughly 10 billion years ago and has been declining since, meaning the radiation environment of the early galaxy was substantially more lethal than the one in which we evolved. The Milky Way itself underwent major merger events, most significantly the Gaia-Enceladus collision roughly 8 to 11 billion years ago, which dynamically heated the stellar disk and destabilized planetary systems across a significant fraction of the galaxy's volume. None of this appears in Hart's calculation. None of it appears in Tipler's. None of it appears in Olson's model. The galaxy in these papers is a passive backdrop, a container of stars rather than a physical system with its own dynamics, its own radiation history, its own merger events. The civilizations they imagine emerging billions of years before us are imagined emerging into a galactic environment that we know, from astrophysics, was significantly more hostile than the one that produced us. The assumption that the same process that took 4.5 billion years on Earth, in a star system that formed in a relatively quiescent period of galactic history, in a relatively calm region of the galactic disk, around a relatively stable and long-lived star, could have run on a comparable timescale in the dynamically violent environment of the early galaxy is not merely undemonstrated. It is in tension with what we actually know about that environment. The galactic habitable zone concept, developed by Lineweaver and colleagues in the early 2000s, gestures toward this problem by noting that the conditions for rocky planet formation with sufficient heavy element abundance only obtained in a particular annular region of the galaxy and only after sufficient stellar generations had enriched the interstellar medium with the necessary metals. But even this framework, which represents one of the more serious attempts to incorporate galactic scale factors into the habitability calculation, does not fully reckon with the dynamical and radiative history of the galaxy as a constraint on the emergence of intelligence specifically. The conditions for life are not the same as the conditions for the uninterrupted multi-billion-year continuity of complex biospheres that intelligence requires. A planet can be habitable in the narrow sense, liquid water, adequate chemistry, stable orbit, while existing in a galactic environment that periodically sterilizes it, destabilizes it, or simply interrupts the evolutionary sequence at a point before the relevant complexity has been achieved. Put the statistical argument and the galactic environment argument together and what you have is not a paradox. You have an explanation. The universe is silent because we are, in all probability, among the first technological civilizations to have emerged in it, not by a narrow margin, not by a few million years, but perhaps by the full span of time that separates the current galactic environment from the one that existed when the first rocky planets formed. The silence is not evidence of a great filter ahead of us, annihilating civilizations before they can build their probes. It is not evidence of a great filter behind us, making the emergence of intelligence so improbable as to be essentially miraculous. It is not evidence of universal civilizational wisdom, or galactic zoos, or anthropic selection effects, or phase transitions in the distribution of cosmic intelligence. It is evidence of something considerably simpler and considerably less dramatic, that the universe has only recently become the kind of place where what we are is possible, and that we are here at approximately the earliest moment that we could be. The other civilizations are not dead. They are not hiding. They have not been consumed by their own machines or filtered out by some developmental bottleneck we are approaching without knowing it. They are here, not here in our sky, not here in our radio telescopes, but here in cosmic time, emerging concurrently across a universe that has only just crossed the threshold their existence requires, as we have crossed it, for the same reasons, on the same schedule. The universe does not grow a single leaf. It grows a canopy. We are not the vanguard of a civilization that never followed. We are one voice in a chorus that has not yet learned it is singing. The machines are not coming. Not because something stopped them. Because no one has had time to build them yet. Class dismissed. Jonathan Brown writes on technology, security, and culture for BorderCyberGroup.com and EthereumArcana.org.